Okay, assume Batman music. Right, take 3. Okay, what is power? So this is your final video on mechanics if you're doing further Maths AS. And this is a small section after everything else we've done, COMEP, WEP, all this kind of stuff. So firstly, what is power? Power is defined as the rate of work, first and foremost. What is work? Remember, work is force times distance. And remember, positive work is the distance moved. Well, when the force has moved the object a certain distance in the direction of the line of the force. So if the force is moving that way and the particle is moving that way, that's positive work done. If the force is moving that way but the particle is actually going this way, then that's negative work done, like when it comes to friction. Now, if W equals Fs, F is obviously a force, so that's newtons. S is a distance, so that's meters. And we know that Newton meters are the same as joules. So when we're talking about moments, we normally use Newton meters. And when we're talking about energy, we're talking about joules. Now, what do we mean by rate of work? Rate of work is that power, but we haven't defined a formula for power, so I'm going to do it here. P equals dV. What is D? D is our driving force. Now, so D is our driving force. Now, the reason I've used D and not F, like the textbooks normally use F, it's because F is normally confused with the resultant force, F equals ma. And that's not what this is. This is the force produced by the engine of, say, a car, which has a corresponding power, like a car does. V, this is just your velocity at that time, okay? So V can be changing, and therefore D will be changing, but P is a fixed power number. So, you know, your engine has a maximum power and it has a range below that, which it can reach. And at any given power time, you'd have a corresponding velocity and a corresponding driving force. Now, as discussed then, what is power? Power is rate of work. Work is W equals Fs. So power, which is dV, D is a force, so therefore that's in newtons, and our velocity is meters per second. So can you see we have Newton meters per second, which is the same as joules per second, otherwise known as watts. So whenever you see a question which mentions rate of work, you're straight into P equals dV, straight into power. If you see anything to do with watts or kilowatts, we're straight into power, P equals dV. Okay, now what benefit does power have to our modeling assumptions? Well, the main thing is that it tells us that velocity is finite now, which is so much better than all of our previous modeling assumptions, where, you know, velocity was just getting to crazy figures because the acceleration just kept going up. Well, that can't happen this time, because if P equals dV, and if I draw this corresponding diagram, so this is a car with a driving force, there's corresponding resistances like air resistance, the friction against the road, okay? Let's think about what happens. So you put your foot down on the pedal, right? You've got your power here. The engine can only reach a maximum power, can't it? A finite number. So this is a finite number, okay? Therefore, if the finite number to make that is D times V, think about it. If D is really, really, really big, then V must be really, really small. You put your foot down on that pedal to generate, you know, that driving force is really high to generate velocity, don't you? So as your velocity is getting bigger, your driving force must be getting smaller because it still has to equal this finite number P. P isn't changing, right? So think about that. As V is getting bigger, D must be getting smaller, you see? Or as D is getting bigger, V must be getting smaller. Now think about it, it's getting faster and faster and faster and faster and faster, but can V be infinitely large? No, because think about it, if V is getting bigger and bigger and D is getting smaller, what's the minimum D can be? It can only be R, can't it? It must be when this thing is going at a constant velocity, because if D was smaller than R, then the resistances would be too big and this thing would start to slow down and would eventually stop. So this is a key bit of theory to remember, that Vmax occurs when your D, your driving force, equals all of your resistance forces. Because it can't be any, it can't be any, what, hang on, I can't, it can't be any smaller than that, otherwise it's going to stop, isn't it? And therefore V has a limiting number. Therefore V has a corresponding maximum, doesn't it? In that situation. So I've just been interrupted like 4 times, and I don't know where I am with the video. I'm not doing it again. So just this is it. Okay, so P equals dV. It helps our modeling assumptions because that makes velocity finite, because when V is at its largest, D must be at its smallest, and D can only be as small as the resistance forces. Let's put that into practice then. So I've got a van. This one's quite straightforward, but it's a good one to kick off with. A van, 1,300 kilos, right? Should put a corresponding normal reaction there. I'm going to write NR because it's talking about constant resistance later, and I don't want to get confused. So the van's engine is working at 27 kilowatts. So the minute I see working at a rate, I'm straight into P equals dV. I'm not writing P equals 27,000. I'm writing P equals dV is 27,000, because I know that that's going to give me something to work with later. Okay, so this therefore has a corresponding driving force, and it's saying there's a constant resistance to motion of 800. So that's where the R is coming in. So I'm putting in 800 newtons there. All right, so that's your air resistance, your friction, all that kind of stuff. So part A, find the acceleration of the van when this thing is at currently 8 meters per second. And remember, that velocity can change, but at the moment it wants us to find the acceleration when this thing is at 8 at the moment. So it makes sense, doesn't it, to like do what we normally do, which is just resolve, because that's how we normally find acceleration. So force to the right is D, 800 is opposing it, we've got our mass and we've got our A. But oh no, I've got 2 unknowns. I've got D and I've got A. So A is the thing I'm trying to find. D, can I get D? Yes, I can, because I can get it from my power equation. So since P equals D times V, and at that moment V is 8, 27,000, then I can find D. So D must be 27,000 divided by 8, so 3375. Great, which means I can plug it into here. So R is going across 3375 minus 800, 1300A, and therefore A would equal minus 800 divided by 400, 1.98 to 3SF. Okay, great, because I haven't used G here, but it's good as standard to be 3 sig figure mechanics. Okay, B says find the maximum speed of the van. We talked about this earlier, didn't we? When do we get Vmax? It's the most important thing to remember with power here. We get Vmax when D equals our resistance forces, i.e. when this thing is in equilibrium and moving at a constant velocity. The velocity can't get any bigger. Okay, so that tells me when P equals dV, right? And V is the thing I'm trying to find. okay, because we know that the power hasn't changed. It's still 27,000. Do I know D? Yes, because resolving left and right, as I've said here, D must equal 800 newtons. So V max must be 27,000 over that D, and D is 800. So our maximum speed, 27,000 divided by 800, must be 33.75 meters per second, or 33.823 SF. Okay? Next example, last example. So this time I've got a car of mass 1,200 going up a slope with 9 degrees. And it's at the moment it says constant speed. Okay, so 9 degrees here. There's my particle, 1200 G. Okay, and what does it say? It says it's working at a rate. So the minute it says that, I'm into P equals dV, 25,000. Calculate the magnitude of the non-gravitational resistances to motion. So it's talking about here, R, that's why I call this NR for these problems. R is our friction, our air resistance all combined, and that's what it wants us to find. On my diagram then, remember I'm keeping speeds off the forces, so I don't get confused with them. It's saying constant speed at the moment of 12 meters per second. Okay. Remember, I need to add my other forces in here so I can get all my information together. So G sine 9 degrees, great. Okay. So P equals dV. Do I know I'm going to need that? Remember, acceleration is 0 here because it told us it's constant speed. So if I resolve first, I'm going to get, see, this is the thing. The minute I've got power, I need to add a driving force in there, don't I? Otherwise, how could that possibly be in equilibrium without a force going up the slope? So we must put in the driving force. The minute I write that, really I should be putting a D on my diagram straight away. So I have D minus R minus 1,200 G sine 9 degrees, right? Equals mass 1,200 times acceleration, which is 0. So I want to find R. I've got a D, which I don't know yet, but I can find it from P equals dV. So P equals D times by our velocity at the time, which is 25,000. So therefore D is 25,000 over 12, which is 6250 over 3, which means I can find R by subbing that into there. So if I rearrange, I get that answer. Take away 12, 9.8, sine 9. And we're there. So we should get 243.66. So 244 to 3 SF. Okay, great. Part B. All right. So that was part A. The rate of working of the engine is now increased. Right. So think about what happens with that. If I'm, at the moment, my velocity was constant. Okay. Which kind of says to me that as it was constant, D equaled all my resistance forces, didn't it? Everything opposing it. That told me that I'm working at V max at that point. But now I increase the power. Think about what's going to happen. You increase the power, the driving force is going to increase, which means your acceleration increases, your velocity then increases. But then what happens as your velocity increases? Your driving force decreases because you've gained speed. You need less. You need less of a driving force to reach that maximum speed because you've already gained speed in that time. So think about what's happening here. The rate of work has gone up to 30. So we're straight into P equals dV, which is 30,000, right? Assuming the resistances to motion are unchanged, so R is still 244, calculate the initial acceleration of the car. So this is what I'm talking about, initial acceleration. So the second we put that foot on the pedal, there's a burst of speed, isn't there? A burst of acceleration. And then that acceleration is going to decrease until you hit the next Vmax. So it's just asking what's that initial burst of acceleration, the microsecond we've put our foot down on the pedal. Okay? So that means, since P equals dV, we need a new D, don't we? We need to know our new driving force. Because we know that at the time, the instant you put your foot down, the velocity was 12. So if I find driving force, my driving force is 30,000 divided by 12, so 2,500, right? Just move this up. So D equals 2,500. Where was that one? Yeah, that was up here. So if D equals 2,500, I'm going to kind of have to modify my diagram a bit, aren't I? Because now I have acceleration. So if I'm resolving up the slope, my driving force is 2,500. Take away my R, which I know is 243 point whatever, because I'm going to use the exact value. Take away 1,200 G sine 9 degrees is total mass 1,200 times by A. And now I can find A. Do you see? We're always moving between P equals dV and resolving when it comes to power. And I had to use, so I'm just going to put that on my calculator now. So 2,500, take away 244, take away 1,200 times 9.8 times sine 9, divide by 1,200. Okay, so we should get 0.347 meters per second squared, and that's the free SF. Okay, must state your accuracy in mechanics. Right, so to sum up then, for part B, for part A you were in equilibrium, you were at Vmax. For part B, we increase the power. We increase the power, that means your driving force increases. That means your acceleration increases just momentarily. And then as your velocity increases, your acceleration decreases, your driving force decreases until you hit Vmax. And when Vmax occurs, that's when D equals all of the forces opposing it. It's in equilibrium, isn't it? Because if D was less than those forces, then it would start to slow down and stop. All right? So for that part B, the initial acceleration, I had to find the driving force. But the key bit is, and a lot of people get stuck on that, well, what's V? V was 12 the instant I put my foot on the accelerator. So that produced this new driving force when suddenly my power in the engine upped. Do you see? It upped the power and therefore upped the driving force. Okay, that's power.